Hello, good people. Welcome to this episode. In this video, I'm going to talk to you about dimensionality reduction with two key algorithms known as PCA, which also stands for Principal Component Analysis, and TSNE, which stands for T-Distributed Stochastic Neighbor Embeddings. Now, you might be wondering, why do we need to talk about dimensionality reduction? And to answer that, I'm going to start by stating a fact which might not be obvious to us because we've never had to spend time thinking about it. But the fact is that we as humans are not able to visualize beyond 3D, okay? So if I ask you to visualize something in 4D or 5D, it becomes difficult for you to do so because our world is actually represented in a 3D space, okay? However, in machine learning, usually the data set that you have to work with in the real world has features that are beyond 3, 4. Sometimes they are in the tens, sometimes in the hundreds, or sometimes even in the thousands. And so it becomes important that we need a way to be able to reduce the number of features in our data set without destroying the patterns in the data set so that we are able to build first of all, visualize our data set to find out if indeed there are some patterns in it which we can build models to internalize and also use those knowledge to make predictions on never seen data. So the advantages to performing dimensionality reduction on your data set are many, but I'm going to share just two with you. So the first one is once you are able to reduce the number of dimensions in your training data set, it becomes easier for you to visualize. And by visualizing, you are able to choose which algorithm you are going to apply to the data set. And the second advantage is since the number of parameters in your model depends on the number of dimensions in your training data set, reducing the dimensionality also has the net effect of reducing the length of time it takes for you to train a model, because the bigger the number of parameters, the longer it takes for training. And so indirectly, it also affects the inference time. So once the model has been built, if there are too many parameters in there, then using that model for prediction or inference is also going to take longer. So these are the two reasons why we perform dimensionality reduction. And I'm going to start off by using an example to teach you. So let me start off by making the usual import. So I'm going to import numpy as np, and I'm going to use some data set from scikit-learn. So sklearn.dataset import load digit. And we will explore this data set in detail. I'm also going to import PCA. So I'll say from sklearn.decomposition import PCA, from sklearn.manifold import TSNE, and I'm going to import numpy as always, and I'm going to import matplotlib.pyplot as plt, and I'll let it do plotting inline. Okay, so I'm going to explain to you both PCA and TSNE, and I'm going to also talk to you about how to use them together, when to use which one, and then we also look at the advantage and the disadvantages of each one of them. So what is this? Import dataset, import, sorry. So this is supposed to be from sklearn. Okay, so from sklearn.dataset import digit. So let's see if this fixes it. Sorry, import numpy as np. Okay, so this should fix it. Great. So first of all, I'm going to show you how to use PCA for dimensionality reduction, and then I'll show you how to use TSNE for the same thing. Let's load the digit. So I'll say digit is equal to load digit. Okay. The digit data set in scikit-learn is made up of handwritten digit from 0 to 9. Okay. and they have been resized into the shape of 8 by 8 pixels. And then each digit is unrolled or raveled into a one-dimensional vector. And so each digit is represented by a 64 element vector. Okay, to prove that, let's see what we can do. Let's inspect something about this data set. And don't forget that every data set is represented as a NumPy array. So everything you know about NumPy arrays apply here. Okay, so I want to get the data set itself. So I'll say x is equal to digit.data. Okay, and then I also want to get the target. Sorry, let me skip this. Okay, so y is equal to digit.target, and then I want us to inspect something about the two values that we have. So we are going to print, let's print s.shape and then y.shape, and let's see what's in there. Okay, so you can see that the X array is made up of 1,797 rows, and then it has 64 columns. And the Y, which is the labels, also has 1,769, which means each row in X has a corresponding label in Y. And the labels are just the numbers 0 to 9. And the entries in X are the pixel values that represent the image for that particular digits. Okay, so it is 8 by 8 pixels, and so when you unroll 8 by 8 pixels into one row, you get 64 values. So that is why the number of columns here is 64. Now, if you got such a data set, the first thing you might want to do is you want to visualize the data set to see if there are patterns in it. For a data set like this, where there are 10 categories running from 0 to 9, the simplest visualization technique you want to perform during the exploratory data analysis phases, you might want to plot a scatter plot to see if there are indeed clusters in your data. But the problem is each row in your data set has 64 columns, and you can't plot a scatter plot that is made up of 64 dimensions. I mean, you only have X, Y, Z dimensions available to you. So the highest you can go to is for 3D plot. And here is the case where you have 64 components for each vector. So how do you deal with being able to visualize this type of data set? And this is when dimensionality reduction comes in handy. And so to be able to visualize, we are going to use principal component analysis, which is a mathematical tool that uses what you know about eigenvalues and eigenvectors and matrix rotation to actually reduce the dimensionality of the data set without destroying a lot of the patterns that are hidden in the data set. Okay, I'm not going to bore you with the mathematical details. I just want to show you how to use these things as tools in your pipeline. Okay, as a data scientist or as a machine learning engineer, you need to have these tools at your fingertip. Okay, so what we do is we first of all create an instance of PCA. So I'm going to create a PCA object, and I'm going to call it PCA, and you specify n component. N component is how many, the dimensions into which you want it to reduce the original data set. So my original data set is made up of 64 columns. I want it to have just 2 columns so that I will be able to make a scatter plot and then see the clusters between the different rows in my data set. Okay, so I'm going to create a principal component analysis object, and I want it to reduce whatever I give it into just 2 columns. Okay, all right, so now that I have this, the next thing that I want to do is I'm going to actually run the PCA algorithm on my data set, which is X. Okay, so once I run the PCA algorithm on my data set, it's going to return me a new NumPy array which has the same number of rows but then 2 columns, because I have specified n component to be equal to 2. Okay, so I'm going to call that X PCA. I mean, that is my X after I have run PCA on it. So I'm going to say PCA.fit transform, and then I'm going to pass in my x. Okay, so let's hit run, and then you see that it has finished running quickly. Now let's check what is in the PCA. So what we can do is I can print xPCA. First of all, let's see the shape. So xPCA, PCA dot shape. Let's see what happens here. So you can see that our data set has been reduced from having 64 columns to having 2 columns, and with 2 columns it is fit for us to plot a scatter plot that is going to show us the different clusters in our data set. So let's go ahead and then make our scatter plot on the next line. So I'll say plt.scatter, and I'm going to scatter spca. I want all the rows and then the first column. So I'm just making a scatter plot of the first column against the second column. Okay, so spca, all the rows and then the second column. And the next thing that I want to do is I want to give a color to each of the points on my scatter plot based on its corresponding label. And remember, we had the labels in the value y. So I'll say my colors should be formed from y. So what matplotlib is going to do is it's going to assign unique colors to each of the targets in y. And so for every entry in in the reduced data set, which is stored in xPCA, it is going to assign a unique color to it based on its class. Okay, so let's make this plot and see what happens here. Okay, so this is PCA that has run on our data set that originally had 64 columns, and it has been able to reduce it to just 2 columns. So we made a scatter plot of the first column on the x-axis and the second column on the y-axis. And so every point, any group of points that have the same color basically belongs to the same class. So you can see that there is this cluster here. There's a cluster that has a color of green, another cluster, and different clusters. It might look like things are mixed up here, but in reality they are not as mixed up as you can see on the plot, because you are trying to plot in 2D space, and then there are too many things in there. If it was on a hyperplane, you could see that there are correct separations between the different clusters. But the whole idea is, with PCA we have been able to reduce the dimensionality from 64 to 2. So at this point we can use xPCA, which is the reduced form of our data set, to build a model. One thing you shouldn't forget, however, is if you use PCA to pre-process your data and build a model out of the reduced form of your data set, then you need to do the same thing when you are making inferences, or when you are applying what a model has learned on a never seen before data set, because the data set that is fed into the trained model should be similar to the data set that is used in training the model itself. Okay, so this is what PCA is able to come up with for us. It is not bad. We are still able to see that there are clusters, there are, natural groupings in the different training examples in our data set. Now I want us to take note of one thing here. Let's take note of how fast PCA was able to run. So if I run it, it is almost like something instantaneous, and the runtime is almost insignificant. We can't really tell how long it took. We can assume maybe it took a second. Okay, now I'm going to let us do the same thing, but this time around we are going to use TSNE, which is T-distributed stochastic neighbor embeddings. It is also another technique. It is a probabilistic technique that helps to reduce the dimensionality of our data sets. So I'm going to create a TSNE object, and I'm going to call TSNE, and I'll specify end component. I want it to reduce into 2. Okay, so let's see where the imports are coming from. PCA is coming from sklearn.decomposition, and TSNE is coming from sklearn.manifold. Okay, so now we have our TSNE object. Let's run TSNE on our X, which is our original data set, and then let's see what it comes up with. So like we did for PCA, I'm going to say s TSNE is equal to tsne.fit transform. Okay, so let's transform this into it. and let's make an inspection. Take note of how long it is taking for TSNE to run. You can see that it is significantly longer than the time it took for PCA to finish. However, the result is going to justify whether it was worth the wait or not. So let's print stsne.shape. And you can see that stsne also has been able to reduce our data set from 64 dimensions into 2 dimensions. Okay, now let's come here. I'm going to copy what I have here, and I'm going to make the same scatter plot, but I'm going to use the result from TSNE. Okay, so I'm going to copy this and I'll replace this with TSNE, stsne, and this should also be stsne. Okay, now let's run it and see the difference. Woo! So you can see that obviously TSNE did a better job with reducing the dimensionality and also keeping the clusters between the different groupings clear enough. You can see that what we got with PCA seemed like, yes, you can see some clusters, but it appears things are a bit mixed up. Okay, but once we use TSNE, you can see that we had proper groupings, and then each cluster is quite far away from the other clusters. Okay, so these are the two different algorithms which we have from classical machine learning, and both of them help us to perform dimensionality reduction. I have explained why we need dimensionality reduction in the first place. So the question is, between these two algorithms, which one do you use? Do you always just decide to go with PCA, or do you go with TSNE simply because the result is more appealing and it does the clustering very well? The answer is it depends. Okay, so first of all, the way to use them together is, first of all, you need to look at the dimensionality of your data set. Over here we saw that our data set has just 64 columns. If you read the documentation of TSNE from sklearn, it tells you that if the dimensionality of your original data set is above 50, then it's advisable that you use PCA to reduce the dimensionality to something either 50 or below, and then you run TSNE on the result of PCA. It just happened that our data set had only 64 columns, so it wasn't too high dimensional. Okay, but if we had a data set that ran into 100 or even 500 or even 1000 columns, then what we want to do is we first of all run PCA on the original data set to reduce it to dimensionality of 50 or below. And once we have the data set in less than or equal to 50 dimensions, we can choose to also run TSNE on it. Of course, if you want to visualize your data set, it has to be in 2 dimensions or maximum 3 dimensions. So you use PCA to reduce the dimensionality to 50, and then you use TSNE to reduce the result of PCA into a dimensionality of 2 or 3. Okay, now let us discuss the differences between PCA and TSNE. So the first thing you need to know is PCA is faster than TSNE. Of course, we saw it when we ran PCA here. It didn't take more than a second for it to finish, but when we ran TSNE, it was very significant. You could see that it took much longer time, and the gains in terms of runtime can be from seconds to hours, depending on the dimensionality of your data set and the number of rows in your data set. So if your data set is highly dimensional and it has a lot more number of rows, then TSNE can actually take a long time to finish. Okay, that is why it's important to use PCA to reduce, and then you run TSNE on the output of PCA. The next thing that I want you to know is that PCA is mathematical and then TSNE is probabilistic. And what that basically means is that if you run TSNE, twice, you are not guaranteed the same output because it is probabilistic. And like the name said, it is t-distributed stochastic. And so there is some stochasticity in there. So the result is never guaranteed. It could be that when I run TSNE here again, and then I make a plot, the plot might be a bit different because it is probabilistic, and so if you run it multiple times, you are not guaranteed to have the same result. So I don't know if we can notice, but the plot we have here is definitely not the same as the plot we had. The groupings and the clusterings are the same. We can see that there are 10 clusters there, but then the actual placement of the points on the scatter plot are going to be different, okay? And another thing you need to know is that PCA is linear, is a linear algorithm, and so it might not be able to represent complex polynomial relationship between features. And so thank you very much for watching, and don't forget to subscribe. I will see you in the next video. If you have any questions, leave them in your comment. Invite your friends to learn from my channel, and keep safe.